All right, so now let's talk about the epoxide opening. And one thing to note is that epoxides act as electrophiles. And so both the carbon-oxygen bonds are polarized towards oxygen. And so if I add a nucleophile, in theory that nucleophile should be able to attack either one of these two carbons. They're both partially positive, and open the epoxide to give me an alcohol. All right, and the reason that epoxides are able to be opened in this way is because the ring, the three-member ring here, is strained, and so because of that, we're able to open that ring up. Now we can do this two ways. The first way is we can use a nucleophile, where we do this in basic media or neutral media. In this case, the nucleophile is just sodium methoxide and then hydrochloric acid at the end to protonate the oxygen once the ring gets open. Or we can do acid promoted ring opening, where in this case the epoxide shown, we first treat it with sulfuric acid to activate it, and then the methoxy group here from the methanol will attack and open the ring. And notice the regiochemistry changes. All right, if you do it under basic conditions, the nucleophile is going to attack the less substituted side. If you do it under acidic conditions, then the nucleophile is going to attack the most substituted side. All right, so here's both of these are the two mechanisms how that happens. And again, under acidic conditions, the most substituted side gets attacked by the nucleophile, and then under basic conditions, the least substituted side gets attacked by the nucleophile. And this follows an SN2 type mechanism, where you have backside attack of your nucleophile at the carbon oxygen bond. Then you break the bond to get here, and then you have a proton source. In a second step, you will just add like an acid or water to protonate here and give you your alcohol. Under acidic conditions, it's a little bit different. First, you protonate oxygen. When you protonate oxygen, you generate this molecule, where now the OH, the oxygen is protonated, has a positive charge. And so this probably follows an SN1 type mechanism, where first this opens, and now this will become a plus charge here, and then the methoxide can come in and attack. Right, so this is step 1, protonation. Step 2 is ring opening, followed by nucleophilic attack. And then in step 3, you just have a deprotonation here by the conjugate base from the sulfuric acid to give you your corresponding alcohol. All right, so you can look at this as many times as you need to. You can also ask questions. So for the experiment that we're going to do, the epoxide opening, this is the reaction, where you have the epoxide that we made from the epoxy chalcone. We're going to treat that with glacial acetic acid for 1 hour. We're going to stir that for 1 hour at room temperature, and then we're going to add in excess water for 30 minutes at room temperature. The resulting product is a diol shown here. Here is my epoxide. The acetic acid is going to provide a proton, and you're going to do proton transfer between the epoxide and the acetic acid. Remember, this is an acidic proton, pK of about 4.76. So the oxygen here is going to deprotonate the acetic acid, and then the conjugate base of the acetic acid is shown here. We call that the acetate anion. Alright, this can also be written as OAC. Alright, so once the proton transfer happens, the epoxide is now activated. So once this is activated, the epoxide is preferentially opened on this side by the water nucleophile, and the reason is because this side has 2 partial positive charges, and so opening on this side, this carbon is a little bit less stable than this one, and so the nucleophile is going to attack at this site. So water in this case is going to be my nucleophile, so that's the excess water that I bring in. That's my nucleophile. That's going to attack this site and cause the ring to open. And so here I have a hydronium ion intermediate, and then the conjugate base of acetic acid can come in and deprotonate water, in this case do proton transfer here between this oxygen and this proton, and then that gives me my product diol, and it reforms my acetic acid. And keep in mind, acetic acid in this case is catalytic, And what that means is that it never gets used up. You will always reform the catalyst at the end of the reaction. So what do we need to do this experiment? We're going to need acetic acid. We need distilled water. We need your epoxy chalcone from last week. We also need 3-to-1 hexane ethyl acetate to do TLC with. That'll be pre-made. As far as supplies, we need a 500 ml beaker. We're going to need a stir plate and a stir bar, vacuum flask, buccal funnel for filtration, filter paper, and a 250 milliliter beaker and watch glass for your TLC chamber. So what's the procedure here? You can see this. I'm not going to go through all of it. The key for the procedure is here. So after we add the water and stir 30 minutes, we need to TLC that crude mixture to make sure that the diol is actually forming. If we don't see the diol, then we have to keep the reaction stirring until the diol actually is actually made. So if the diol is not there, we keep stirring. If the diol is there, then we can filter and then let the solid dry until next week. And then next week we're going to compare the melting points as well as the TLC for the diol and the epoxy chalcone. So this is a TLC plate from a previous experiment. This is where the diol is. This is where the epoxide normally shows up. And I want you to answer this question before coming to lab to explain why the diol has a much lower RF than the epoxide.